Alright, so this part is about reaction kinetics. So in this video we are going to be looking at a reaction where we have reactants forming products. So let's suppose we have reactants A and B. So we have reactants A and B to form products, and the product is P. So rate of this reaction, the rate of reaction is given by the formula rate is equal to K, then the concentration of reactants. So in this case, the concentration of A and the concentration of B. But now, to the power M, the concentration of A to the power M, and the concentration of B to the power Y. So M and, let me put N instead of Y. So M and N do not depend on the stoichiometry, or do not depend on the coefficients. Do not depend on the coefficients that are put in front here. For example, if we do this equation again, like 2A plus B to give us P, we are going to still have rate is equal to KAM and B to the power N. So let us take note of that. Now let's use this information in the reaction given here. So consider the reaction 2HBr to form H2 and Br2. So we have about 3 problems that we are going to solve using that reaction. A, this one should be B. Express the rate of reaction in terms of change in concentration of each of the reactants and products. B, in the first 25 seconds of this reaction, the concentration of HBr dropped from 0.6 m to 0.152 m. Calculate the average rate of reaction during this interval. So let's solve the first problem, A. So this is our reaction again, just repeating the reaction. Express the rate of reaction in terms of change in concentration of each reactants and product. So for this reaction, the rate is given as negative 1/2. The 2 is coming from here. Negative 1/2 change in concentration of HBr. So the negative in front here is just showing that it is the rate of reactant. It is showing that the reactants are being consumed. So rate is given as change in concentration, and because it is rate, divide by change in time. But you can see the 2 down here indicating that we have 2 in front of HBr. So this rate is equal to, now we have 1 in front here, so we don't show it, and we also have 1 in front here. So, and we are forming products. So the rate is equal to negative half change in concentration of HBr over change in concentration over change in time. So this one is equal to change in concentration of hydrogen over change in time, especially that we have only one hydrogen here, which is equal to change in concentration of bromine divided by change in time. So if you look at the hydrogen and bromine, we have positive in front of it, in front of them, because they are products. So in this kind of rate, reactants have a negative in front. Products have a positive in front. So if you want to express this in terms of change in concentration of each reactant and product, we see that rate is given by negative half change in concentration of HBr change in time is equal to plus change in concentration of H2 change in time is equal to plus change in concentration of Br2 over change in time. So we have expressed this. We expressed rates in terms of change in concentration. Now let's solve a problem based on that. So the same reaction, now we go to B. In the first 25.0 seconds of this reaction, the concentration of HBr dropped from 0.6 to 0.152. Calculate the average rate of the reaction during this interval. So just a reminder, what we had is at the beginning we say rate is given by negative half change in concentration of HBr time is equal to change in concentration of H2 over change in time is equal to change in concentration of Br2 over change in time. So, but in this case, what we want to find out is only this part, because we are given the concentration of HBr. We are not concerned with the other rates. So we can say the rate of this reaction is given by negative half change in concentration of HBr divided by change in time. So what do we have? The change in we are going to have still half here, and up here we need to have change in concentration. This one is initial concentration, this one is final concentration. So the change in concentration must be given by final minus initial. So which is 0.152 minus 0.600 molar. That's the change in concentration. And the change in time is given here, 25 seconds. So 25 seconds. So when you multiply this problem, you are going to have 0.00896 molar per second. So this is the average rate of this reaction. Now let's look at the same problem, but the C part, the third part of this problem. So I will start with the equation again. The equation is 2HBr gas to form H2 gas plus Br2 gas. So it's saying predict the rate of change of Br2 during the same interval. In this case, it is the 25 seconds interval. So we are looking at this one. So since this is a product, we are going to say rate is equal to change in concentration of Br over change in time. And another thing that we need to take note is every rate of change, for a specific reactant or product is given as change in concentration versus delta T. So let me just make a change here. So it's given as change in A over delta T. But we don't have coefficients here. We don't have half or something like that. So this is rate of change of something. So the question again, predict the rate of change of Br2 during the same time interval. So we are saying rate of reaction. So I should say rate of reaction so rate of this reaction is given by delta change in Br2 over change in time. That's what the rate is given by. But we know from the previous equation that the general rate of this reaction is 0.00896 molar per second. Now, because here it's saying predict the rate of change of Br, rate of change of Br2 is also given as change in Br2 divided by change in time. So in this case, the rate of change is also 0.00896 molar per second. So why is the rate of reaction the same as the rate of change of Br? The answer is because Br2 does not have a coefficient, does not have a coefficient. So as such, its rate of change will be equal to rate of reaction. So its rate of change will be equal to the rate of reaction. That's why we see that the rate of reaction and the rate of change of BR is the same. Now let's look at another problem. So consider the reaction given here. Consider the following reaction. So this is our reaction. If the rate of this reaction is 0.01 molar per second, I'll get rid of this. What are the rates of consumption of H2S and O2, and the rates of formation of H2O and S8? So we see that we are consuming this and this. We are forming this and this one. So that's what we are doing. So the first way to solve this problem, we start with rate is equal to negative 1/8, because we are using the coefficients. Negative 1/8 change in concentration of H2S divided by change in time is equal to negative 1/4, because the coefficient here is 4, change in concentration of oxygen over change in time. So we are putting negatives here in front because these two are reactants. Now when you go to the products, you have 1/8 change in concentration of water divided by change in time, which is equal to change in concentration of S8 divided by change in time. So that's what the rate of this reaction will be. But we are saying that the rate of this reaction is 0.010 molar per second. So that is the rate of this reaction. So the question is, what are the rates of consumption of H2S and O2, and the rates of formation of H2O and S8? So let's look at consumption of H2S. So this one, the rate of consumption of H2S will be given based on, so rate is equal to negative 1/8 change in concentration H2S divided by change in time. That is rate of reaction. So I'll add a reaction here. But rate of consumption. So rate of consumption is only this part. We don't have 1/8 there. So what we are looking for is just delta change in concentration of H2S over change in T. That's what we are looking for. So what we are going to say is change in concentration of S over change in time is equal to minus, because we multiply this 8 times rate here, and then minus will transfer that side. So minus 8 times rate of reaction. So we are saying rate of consumption, you just give the change in concentration over change in time. You don't have the coefficients in there. So to get rid of this coefficient, you need to multiply both sides by the coefficient. That's what we have here, negative 8 times rate of reaction, which in this case is negative 8 times 0.010 ms. So which gives us 0.080 molar per second. So this is the rate of consumption of H2S. Now what about the rate of consumption of oxygen? Now let me get more slides. So we looked at the rate of consumption of this. Now we want to look at the rate of consumption of oxygen. So as usual, we said rate in this case is given by minus 1 over 4 change in concentration of oxygen divided by change in time. But consumption of oxygen is given by only change in concentration of oxygen over change in time. So that's the rate of consumption of oxygen. So we remove the coefficient. So if we are using this one, we are going to say rate of consumption of oxygen is equal to negative 4 times rate of reaction. In this case, which is negative 4 times our rate of reaction was 0.010 molar per second, which is negative 0.040 molar per second. So we can say that the rate of consumption of oxygen is equal to negative 0.040 molar per second. Now let's go on and look at the rate of formation of water. Now we are going here. What is the rate of formation of water? So we look at this and we see that we have a coefficient 8 here. That's what we are going to use. So as usual, we say rate of reaction is equal to 1 over 8. So you can add plus here if you want. 1 over 8 change in concentration of water over change in concentration or over change in time. But here, rate of consumption Rate of consumption is equal to just change in concentration of water over change in time. That's what we want. So if we use this formula here, we say the rate of consumption of water is equal to 8 times rate of reaction. And we know that that is 8 times 0.010 molar second, which is equal to 0.080 molar second. So we can say that the rate of consumption of water is 0.080 molar per second. So the difference between rate of reaction and rate of consumption or rate of formation is that rate of reaction has coefficients. Rate of formation or rate of consumption do not have coefficients. So I want you to be able to do the last one here. What is the rate of formation of S8? So you can do that on your own. Let's move to another problem. So let's consider the reaction here. As shown. And what we want to do is we want to determine the expression of the rate law. So what we are looking for, we want to have something like rate is equal to K CHCl3 M and then Cl2 N. That's what we want. So rate is always given. This equation is always given using reactants. So equation always given using reactants. So let's see what we have here. So you are given concentrations. You have conducted an experiment and you are given concentrations. So you have several experiments. Experiment 1, 2, 3, and 4. And you are given different concentrations from that experiment. This is concentration of CHCl3, concentration of Cl2. And these are what we call initial rates of reaction. So these are the results of the rates of reaction. So the question is, what is the rate law of this reaction? So what is the rate law of this reaction? In other words, what is this expression for this reaction? That's what the question is about. So let's see how we are going to solve it. So to solve this problem, we look at the reactions that we are given. We have 4 reactions here, but we have 2 reactants. This is reactant 1, this is reactant 2. Or we can say this is reactant A, this is reactant B. So we have two reactants there. So what we do is we isolate one reactant. We change the concentration of one reactant and leave the other reactant intact. For example, here, for reactant A, you can see that we have multiplied this reactant by 2 to move from 0.01 to 0.02. But we have multiplied by 1, so we have not changed this reactant. So as you can see, as we change this reactant, we also see that the initial rate has changed from 0.0035 to 0.0069. So we have seen an increase in the initial rate as we change this reactant here. So what do we do? What we do is we say rate of reaction 1 or rate of reaction 2, which is this one, divided by rate of reaction 1, which is this one. So we divide the two rates. Now when you divide the two rates, what you are doing is you are dividing these two. So 0.0069 divided by 0.0035. So you have divided the two rates. Now we know that rate is given by, in this case, K, the concentration of CHCl3, M, concentration of Cl2N. So when you divide this, every other thing cancels. What you remain with is the concentration here of CHCl3 to the power M divided by the concentration of CHCl3 to the power M. But this is for reaction 2, this is for reaction 1. Now you can, instead of concentration as written like this, you can use numbers. So 0.02 to the power M over 0.01 to the power M. But this one can be written as 0.02 over 0.01 to the power M. Or in other words, 2 to the power M. So we are saying rate over 2 divided by rate over 1 is equal to 2 to the power M. So here, this one, these two, when you divide them, you get about 2. So 2 from here is equal to 2 to the power M from here. Because you are dividing two numbers. Here you are dividing the rates, here you are dividing the concentrations. So by law of indices, here this one can as well be 2 to the power 1 is equal to 2 to the power M, which means that M is equal to 1. So that is by law of indices, because this one is there although we can't see it. So what we are saying is, for this reaction, we have rate is equal to K CH Cl3 1 here and Cl2 N. But now we don't know what the N is. So another way of solving this one is to say 2m is equal to 2. So you can say log the logarithm of 2m, which is equal to m log 2 is equal, because this one can transfer to the front here because it's an index. So that the m log 2 is equal to log 2. So we just took logarithms of both sides. So log 2m is equal to log 2. So that is the case. M log 2 is equal to log 2. So if you take this one, you divide both sides by log 2 to get rid of the logarithm. You find that this part is 1, this part is m. You find that m is equal to 1. So we are just saying that our m here is equal to 1, and then we just change this m to become 1. Now, how do we get the n? So we come back to the same equation. So the first part, we changed this, we used these ones. For the first part, we used these ones. We cannot use these because we did not use these because here for Cl2 we start with 0.1, 0.01, and then we end with 0.01. So this one was constant, no change here. Now this time around, we already have this one. We already solved for this. Now we want to solve for this. So let me just get rid of this one and see what change I'm going to make. See what change I'm going to make. So if I go down this reaction here, we see that here there is no change. This is times 1, so there is no change. But between this and this, we see that there is times 2. So there is a change in concentration from experiment 2 to experiment 3. There is a change in concentration. So what we are saying is, we can look at the rate, the change in concentration here, and look at the change in rate here. So this part will give you change in concentration, while this part gives you change in rate. Now how does it go? So we'll look at this reaction. The reactions we have taken reaction 3 and reaction 2. So I'll say rate 3 divided by rate 2, which is 0.0098 divided by 0.0069. So these are the two rates that we are dividing. But these two rates, remember, we have rate is equal to K CH Cl3 1 here and Cl2 N. So this is what we are looking for, the N part. So this one is equal to, now this one will come from these concentrations, is equal to 0.02 over 0.01 to the power N, which is equal to 2N. So what we are saying, you need to divide this one and find the answer. So when we do that, we say rate 3 divided by rate 2 is equal to this divided by this one. And that will give us so what is the answer for this one? This gives us 1.42. So 1.42 is equal to this 2N, 2 to the power N. So what we want is, we want to find what N is. So how do we go about that? So to solve this problem, we have to take logarithms of both sides. So we say log 1.42 is equal to log 2 to the power N. But log 2 to the power N is the same as N log 2, because this one can transfer to this position. So what we are saying is N log 2 is equal to log 1.42. Then what we do is we divide both sides by log 2 so that N is on its own by log 2. You can use calculator for this. Actually, you should use calculator for that. So this cancels each other, and then N is equal to 0.50, which is equal to half. So what we are saying is N is equal to half, which means here you are going to put half up here. So for this one, we can write the final equation. We say rate is equal to K CH Cl3 and Cl2 half. So that is the rate law for this reaction. So what you do is you just make sure that you change one of the reactants and you leave the other reactant constant, and then divide the two rates. Then afterwards you change the second reactant and leave the other the first reactant constant, and divide the rate change and get the M and N as we have done in this reaction. Thank you.